Hello and welcome to the Boston Structural Heart YouTube channel. Today we are going to go over a very precise, focused and a short presentation on a very challenging topic but of a huge clinical interest, and that's the three-dimensional quantification of right ventricle. To start off, here are my disclosures. I make educational materials for both GE ultrasound as well as Abbott Medical Systems, and of course I own this free educational resource, the YouTube channel Boston Structural Heart, that you're all tuned in right now. So the outline of our talk is very simple. We're going to go over the anatomy, the physiology, and the available methods of assessment of three-dimensional imaging and as well as three-dimensional quantification of right ventricle. Now first, let's go over the anatomy. The anatomy of the right ventricle is actually pretty complicated as opposed to the left ventricle, which is just two papillary muscles, a few trabeculations, and atrioventricular valves. It has just about 10 or more structures of extreme anatomical and physiological importance, and it is famously said about, as it is famously said about the omental anatomy, that it is very easy to visualize and understand its orientation. It is easy to imagine the relationships and the reflections of the omentum, but they're very difficult or almost impossible to draw on a flat piece of paper how the omental reflections relate to the three-dimensional anatomy of the intestine and the internal structures of the abdomen. Now the same goes for the right ventricle. It is something that you can see and how it wraps around the left ventricle. You can imagine the way it is oriented in the heart, but it is very difficult to draw this anatomy from a single perspective because it looks pretty different from different angles and different perspectives. As you can see, specifically, it has a pulmonic valve, an annulus, crista supraventricularis, RV anterior wall, the trabecular septum, then the medial and the anterior papillary muscles, and sometimes more papillary muscles. But if you divide all of it, it essentially consists of three portions. One is the infundibulum, the inflow of the right ventricle, and finally the trabeculated apex, which is also very difficult to visualize echocardiographically. Now, looking at it, again, the description that it looks different from different angles. On the left is a drawing of a right ventricle which appears crescentic and wrapped around the left ventricle. When you look at it en face, it looks like a very small cavity if you look at it in a Valentino description of cardiac anatomy that we have addressed in another lecture. And the most important thing, this is one of the dissections that we did in our lab on a porcine cardiac model. You can see in one angle, it looks like it is wrapping around the left ventricle. And another way of description, or going in another perspective of the dissection of the right ventricle, it looks like a triangular trapdoor that opens and closes like this as opposed to being wrapped around. Look at it, the same perspective can be gained from a transgastric view with a slight angulation of the probe. You can see on the one angle on the left, it looks like a crescentic wraparound structure around the left ventricle, and a little angulation of the scan plane, and you can see it looks very specifically triangular with the tricuspid valve opening into the right ventricle on this side. You're looking at the imaging of the right ventricle in three dimensions. You can see in the right side the four-chamber view, which looks pretty straightforward, side by side with the left ventricle. However, when you look at on a three-dimensional perspective of a transgastric image of the right ventricle, you can see the RV inflow, the outflow, the infundibulum of the right ventricle. This is the interventricular septum, and this is also famously called the monkey face appearance. We have two eyes and the nose and the facial opening, which is the mitral valve. But the important thing to pay attention over here is that both the inflow and outflow are on opposite sides of the infundibulum of the right ventricle. So it has to go through the blood, the vorticial flow of the blood has to go through a very complicated a channel or complicated track from the inflow of the tricuspid valve at this location to go out of the pulmonic valve in this direction. Now this brings into question, how does this all happen and how is it able to do this one? So this is a very precise slide about the physiological and anatomical differences between the right and the left ventricle. You can see that the two most important differences are volume, which it has more volume than the left ventricle. It has less mass, but it has smaller ejection fraction. And the most important thing which determines its physiology, it's elastance and compliance. Elastance is its ability to resist a change in the shape, which is very low in the right ventricle, which implies that it is a highly compliant chamber, which means it changes a lot in volume for a change in pressure, as opposed to left ventricle, which has a very high elastance and very low compliance. So predictably, the left ventricle responds and adapts better to higher pressure, as opposed to the right ventricle, which adapts and responds better to volume than pressure. Now, another fundamental difference between these two ventricles is in their stroke work. On the left, in this situation, you can see that we have a distinct stroke volume, pressure volume loop with an isovolumetric contraction time, the ejection phase, IVRT, and the eventual diastolic filling phase, with very distinct and well-defined isovolumetric contraction and relaxation points. As opposed to that, the right ventricular pressure volume loop is triangular in its shape, implying that there are no well-defined isovolumetric contraction or relaxation phases, which means it continues to fill during diastole and continues to eject during systole. That's one of the most fundamental differences of energy consumption being more optimal on the right ventricular side, because it does not have IVCT and IVRT periods. Now, right ventricular function cannot and should not be seen in isolation from the structures that it is surrounded with. Most important of that is the interventricular septum, because of the wraparound of the right ventricular leads to a contribution by the interventricular septum into the radial shortening of the right ventricle, leading to a generation of transseptal pressure to the point that it is assumed and it is believed that almost 30% of the right ventricular contractile force is generated by the left ventricle. We go on and say the other important structure that it determines and impacts the right ventricular function is the pulmonary vascular resistance. And the right ventricular changes significantly during the course of a respiratory cycle also, which means when the PVR is lowest at the functional residual capacity, the right ventricular faces the least amount of afterload and therefore has the highest ejection fraction at end expiration. And at the vital capacity level of breaths, at the highest levels of inspiration, when the pulmonary vascular resistance is maximum, right ventricular ejection fraction takes a significant hit at that time. So it is so compliant that even the changes in pulmonary vascular resistance with inspiration and expiration also impact right ventricular function. Then we go on to the most important part, that's why we're here, and that's the available techniques of right ventricular volume assessment with 3 dimensions. Now, this is quantification of right ventricle, predictably because of its complex anatomy and function is a pretty complicated undertaking. It requires an understanding of its unique structure and the functions and the limitations of assumptions of area length methods of determining and estimating volume. It is, again, as we talked about, is a very sensitive chamber. It is both affected by the lungs, the left ventricle, as well as the pericardium. Its models of its assessment are based on assumptions of geometry, are definitely prone to error because it doesn't follow a predictable geometry in base, mid, and the apical regions. 3D imaging, which is automated, which we'll discuss, does offer some promise, better than these models based on geometric assumptions. And the current status, as we look at it right now, we all know, we talk a lot of big game about these 3-dimensional quantifications is purely based on visual qualitative assessment of the size of the right ventricle. So of the various methods, and geography, which is no longer used because of the exposure hazard, as moderate accuracy. 2-dimensional ultrasound is inaccurate for quantitative analysis, requires manual tracings and multiple views to account for the limitations of geometric assumptions. Magnetic resonance imaging is considered the gold standard in manual tracings, and it has also automated segmentation methods. And lastly is the 3-dimensional ultrasound or echocardiography, which was initially part of a manual tracing in multiple views with automated segmentation, and now we are on to the artificial intelligence-based algorithms that we will discuss in the next few slides, has offered the most promise and has demonstrated that it is actually one of the most accurate methods of doing this thing. So one of the best systems is the TomTec imaging systems that I don't have any commercial affiliation. I think it's one of the best and one of the first systems that was based on artificial intelligence of automated structure recognition and tracking, in the various frames of systole and diastole acquired over an R-wave gated acquisition that has offered the most promise and set the standard. So the steps of doing a three-dimensional quantification of the right ventricle consists of, number one, is to acquire an R-wave gated multibeat acquisition, which has, although it's not live, but it has the highest frame rate as well as the highest line density, which means the best of spatial and temporal resolution. Now that's a limitation of this method, because now, which implies that you can only do this quantification in patients with stable rhythms and with lack of electrical interference of motion artifact because of patient motion. So that's a huge limitation of this one. You have to include the entire tricuspid and mitral annulus, because the algorithm is based on identifying both the annuli, the middle portion, and the apex, and then reconstructing the right ventricle in and around this thing. And we have to have the apex available, because in the image, as you can see in this one, you have the tricuspid annulus, the mitral annulus, the LV apex, and the right ventricular apex, all in the same, because these are the fundamental points around which the software reconstructs everything. So the next function after that is, of all the available softwares in this, 4D Cardio View is the name of the software, and it has a drop-down list of multiple softwares. When you open the software, you have to go to the 4D RV function to tell the software that we are going to be looking and reconstructing the right ventricle over here. Once you have done that, then you have the visual feedback or graphic feedback to align all these views in the same fashion. For example, number one, which is this over here, has to have this portion in the left atrium, and this should be designed to the apex of the left ventricle. Similarly, this is the top. Again, three views are to align the left ventricle in this specific fashion, and the lower three views are to align the right ventricle based on this volume. So the top three are to look at the left ventricle and to align the apex with the middle of the left ventricle, and this one is to align the apex of the right ventricle with the middle of the right atrium. As you can see, you can derive the visual feedback based on these graphics that are present on the side. I mean, there are certain manual adjustments you can do for brightness and contrast, and to flip the images and to segment it so that you can see the boundaries much more easily are possible, but that's marginal. But most of the impact of the quality of this assessment is based on how great the image you acquired in the first place, which means how high is the frame rate and how high is the spatial resolution. Now, in this rather long video, you will see that the top three images, we are going to be aligning the mitral valve with the apex. In the lower ones, we are going to be aligning the tricuspid valve with the right ventricular apex. And it doesn't really matter in which order you do this thing. It corrects itself for this thing in and around all these images. Now you can see on the left, we have aligned the left ventricle with the apex of the center of the mitral valve in three views. And in these three views, we align the tricuspid valve with the apex of the right ventricle. Again, the tricuspid valve, the apex of the right ventricle. And in this one, we are going to be using this transverse image to bring it to show the short axis width of the right ventricle in the transgastric position image, which is analogous to the transgastric position. We'll do that. It is almost there. I'm going to scrub through this to make it, as you can see, this is being dragged over here now and is being brought to conform to the width of the right ventricle. And now we have it all aligned in one space, in one line. After this is done, as you can see, now we have all these images aligned in the same fashion as these things are. After this is done, the right ventricle and the left ventricle are both segmented, which means all the unnecessary portions are removed. The images are tracked, and you can see that this does a pretty decent job, which is referred to as the butyl revision or static contour revision, because you have the ability to manually correct for any incorrect assumptions made by the software, and you can see if it is not tracking it, you can manually correct for that tracking. But most of the time, if you have a great image, it doesn't really matter. Lastly, as it is done, the analysis is done, and you tend to get an diastolic volume and systolic volume, the stroke volume, the ejection fraction, and even the longitudinal strain, both in the septum as well as the free wall, can be achieved. Again, as you can see, you can correct for any both in end-systole and end-diastole, as well as the intervening images. For incorrect tracings done by the software, you can manually correct them. Once you have everything all sorted out, you can get a graphic representation of what it looks like, which means you have the end-diastolic volume, systolic volume, ejection fraction, and the strain. And this is has a pretty accurate reproducibility, both inter and intra-observer variability, and the volumes and the ejection fractions obtained through these techniques have shown to be much correlate very well with the ones obtained with MRI. So this is actually a very decent and a great way of assessing the volume of the right ventricle. It may have taken a couple of minutes because I was walking through very slowly, but once you are in the operating room and you want to do something, it takes usually less than a minute after you acquired the image to do an automated analysis of this one. So this is a great volume time plot that you get out of this one. So at the end of the day, you have something referred to as a butyl, which shows the RV inflow, outflow, as well as contraction of the free wall and the right ventricle. Now, everybody asks what the clinical application of this. And so what we've been doing in our medical center is using PA catheters, which are with a pace port, to be placed in the right ventricle and to measure continuously the right ventricle as we measure the PA catheter. And we superimpose the right ventricular pressure as it measured in the patient with the PA pressure port in this location. And once we do that, once we have the pressure that we are generating from the right ventricle, we have the volume that we are generating for the right ventricle, and we have the duration of the cardiac cycle based on the EKG, now we can draw what we refer to as a pressure-volume relationship between the increase in the pressure and the decrease in volume to generate a right ventricular pressure-volume loop in real time, near real-time generation of a right ventricular pressure-volume loop, knowing whatever non-existence isovolumetric contraction and relaxation, as you can see physiologically, the same actual as the time is decreasing, the pressure is decreasing, and the volume changes at the same time as the time in right ventricle, and you tend to have a triangular pressure-volume relationship. We are soon going to publish these results with from our group. That is another way of looking at a very objective analysis of right ventricle, and that's generating near real-time pressure-volume relationships, and the changes in it can also be tracked with different therapies, valve replacement, repairs, and see how sometimes subtly there are changes in right ventricular function and volume and pressure relationship that are often missed with naked eye observation, or just looking at the gross two-dimensional images and wall motion of the right ventricle. So at the end of the day, there are multiple other vendors who are coming out with similar techniques of using the right ventricle, because this is the impact of right ventricular dysfunction on outcome is being appreciated, and therefore this is a very exciting new area of research that we have started participating in to improve patient care and outcomes. I hope you like this lecture. There's more to follow on the right ventricular function assessment in the coming days and months. Stay tuned. Thank you very much.